I will try to give some combinatorial and algorithmic insights about graphs that can be covered by k shortest path. And here you should think of k as being a small parameter, much smaller than the number of vertices of the graph. And speaking of shortest path, so Orléans is 120 kilometers south of Paris, like 1 hour by train. Okay, so here are the problems that I will mention. So I'm given a graph, and the question is, can I cover all the vertices of the graphs with at most k shortest path? So that's sometimes called isometric path cover. So here for this input, oops, sorry, my bad. So for this graph, I can cover it with 3 shortest paths. I will use different colors for the path. It will be more visible this way. You see that here I don't cover one of the edges. So I have the version where I need to cover the vertices, or the version where I simply want to cover the edges. For the same input graph, if I ask, can I cover it by k shortest path, in the sense of covering all the edges, I need four different paths. So actually, all throughout my talk, I will mention only the edge version, at least for the proofs, but all results extend to the vertex version. But proofs will be simpler for edges. Okay, so of course, a natural thing to ask would be, given this input, the graph and parameter k, can I solve the problem, or how fast can I solve the problem? Of course, the problems are NP hard by an easy reduction from dominating set. And let me also introduce a different version. For now, it's just a technical difference, just a technicality, but it will make a difference in the future. So assume that I'm not only given graph G and parameter K, but I'm also given the pairs of terminals. I want the shortest path to join, for example, these two red vertices and these two blue vertices and these two yellow vertices. So the terminal vertices are specified in these versions, and I simply call them isometric path cover or edge cover with terminals. So here, if I'm given, oops, again, sorry. If I'm given that, it might make a change. It will make a change in the future. So since I said that the problems aren't hard, what am I planning to do? So as I said, k for me, the number of paths, is a small parameter. And if you are familiar with parameterized complexity, when you have NP hard problems and when we think of a parameter as being small, we would like to have algorithms which are called fixed parameter tractable. That means that we would like the running time to be a polynomial in n, and this polynomial, the degree of the polynomial, should not depend on the parameter. And of course, we expect some exponential function, at least computable function, depending on parameter k. So we want to restrict this exponential explosion to parameter k, not to the size of the input graph. So that's what we are looking for. We are looking for FPT algorithms, and if we can't, sorry, here is a typo. If we only have algorithms in time n to some function of k, so n to the k, n to the k square, something like that, we call these algorithms XP. So what I will want to address in this talk is the following: are problems isometric path cover, edge and vertex version, FPT, are they XP with respect to parameter k, and the same for the versions with terminals. And here are the results. I think the funniest part, the most entertaining part of this work was to do the combinatorial bounds. So actually, we proved the following: that if a graph G is coverable by k shortest path, then if you start from any vertex A and you look at all vertices that are at a given distance d from A, the number of these vertices is upper bounded by a function in k. So how it doesn't depend on n, on the size of the graph, it only depends on parameter k. And actually, the proof is pretty simple for the edge version. I will even show you in the stock the proof which is with a factorial bound. I don't think I will show you the proof with a simple exponential bound, but you can find it on archive. And it works nicely for edges. For vertices, it's a bit more tedious, and it adds a polynomial factor here in K. Now, we have a kind of weird corollary that due to that, the tree width of our graphs of yes instances is upper bounded by a function of K, twice this function that I mentioned before. And actually, that is very, very easy. I don't know how familiar you are with tree width and path width and stuff like that. So I'm not planning to get into detailed definitions, but let me picture the situation. So I said that if we have a yes instance, if we start from some vertex A, and if we do a breadth-first search, then on each layer, the number of vertices on the same layer is bounded by this function that I call g of k. With this, I construct what is called the path decomposition of the graph. What do? I simply take bags. Bags are vertex subsets, and bags are my bags will be formed by 2 consecutive layers. So I have the bag with layer 0 and 1, the bag with layer 1 and 2, and so on and so forth. And this is a path decomposition. So in general, a path decomposition is a sequence of bags such that each edge has both endpoints in one bag. And for each vertex, the bags containing the vertex form a consecutive subsequence of the whole sequence. So here's the fact that this is a path decomposition is completely trivial. And the width of a path decomposition is the size of the largest bag, actually -1. So here, if I bound the number of vertices in each layer, the size of the bags is twice this number. So the path width is trivially bounded. And if I have this, so once I prove theorem 1, which I will do later, I have that the path decomposition of yes instances is very low, is bounded by a constant depending on k. And then I use this powerful machinery of Courcelle to show that problem isometric path cover with terminals, edge and vertices version, these problems are FPT. So the running time is of type f of k times it's even linear in n. And here is how I do it. As I said, if I have a yes instance, it must have a path decomposition of small width. I just do the BFS and I check if the number of vertices in a layer exceed my prediction, then it's a no instance. If so, I know that I have this path decomposition, tree decomposition, whatever, and then I will use this machinery of Courcelle that I will tell just a word in a minute. So it works if I have the terminals. If I don't have the terminals, the best I can do, the best we know to do, we can do is to guess them. So basically, I need something in times like n to the 2k and an extra time. So it only gives an XP algorithm, and I don't know if the problems are FPT or not. I can only show that they are XP. I don't have hardness proofs either. Okay, so I'm not getting into the machinery of Courcelle, but it says that every problem that is expressible in some type of logic can be solved in a time n times some function of the tree width or path width of the graph. And it also says that you can do optimization on some problems. And basically, what we do for this isometric path cover with terminals is that, okay, we compute this decomposition by BFS. If it's too large, we answer no. It's a no instance. If the width, if parameter w is small enough, then we express this question of finding path P1 to Pk, so such that P1 joins vertex 1 and source 1 to target 1, path 2, source 2 to target 2, and so on and so forth. And we minimize the sum of the length of the path. Actually, we minimize the number of the total number of edges that we used in all these k paths. And this is easily doable by a MSOL formula. And we just need to conclude that. So we do this, we use this optimization tool. We look at the optimum. And if the optimum turns out to be exactly the sum of the distances between the pairs of vertices, then we know it's a yes instance. And if it's not, we know it's a no instance. So that's how the algorithm works. So we just use to sell as a black box. Okay, so let me go back to my combinatorial part, which is I think the most interesting one. Again, I assume that I'm given a yes instance, and I also only speak of edge coverings. So I have a graph that is coverable by k shortest path here. K is 6 on my example. I give one color to each path to make it nicer, and I also choose an orientation. I just choose a direction on each of the paths. I put an arrow like that. Okay, and by definition, if I'm in a yes instance, each edge will be covered by at least one of these paths. So we'll have at least one color. In my example, each edge has exactly one color, but of course this is a particular case. Now, if I look at one path here, for example, the path that is bold. If I take one path from A to B, okay, this path goes through a sequence of edges, and I think of my path as oriented as from A to B in that direction, and then I can say that okay, this path uses a yellow edge in the positive sense, meaning that it follows the yellow path according to its direction, then a second edge in the positive sense, then the purple, then we go to purple edge, but in the opposite direction, because we go upwards and the path goes down, and so on. So it's purple minus, red plus, red plus. So that would be a coloring of the edges, a possible coloring of the edges of my path that I fixed. Okay, that's just the definition. And now the very easy observation is the following. I say that the path is well colored if I can color the edges such that the edges with the same color induce a connected subpath. So I don't want to have blue, red, blue. Okay. And the trivial observation is that if I have a shortest AB path, I can make it well colored. Why is that? Assume that that I have a shortest AB path, which is not well colored, because I have somewhere an edge colored blue, and then another color, and then later another edge color blue. So my blue color is not connected. Then it means that this vertex X and this vertex Y are both on the blue shortest path. So I can replace all this dotted subpart with a blue path. It cannot make it longer, since blue is the shortest path. So doing that, I reduce the number of colors used for my I could have changed the path from A to B, but it's still a shortest path from A to B with less colors than initial. So this proves that for any pair of vertices, there is a shortest path connecting them, which is well colored, or which admits a well color, a good coloring. Okay, so that was my first observation. And now if I consider a well-colored shortest path, I know that they follow. So for example, I know that I have, it starts with yellow, then, and in the positive sense, then with purple in the negative sense, in the opposite negative sense, and then with red in positive sense. And I don't count how many purple edges it has. I just say it's a sequence of yellow plus, purple minus, red plus. So to each well-colored path, I can associate what I call the color sign word. And let me note that this word is of length at most k. It has no repetitions. And the letters, I mean, I have at most 2k letters because I have the k colors with a plus or minus sign. So at least it's obvious that the number of such words is bounded by a function in k. So, okay, whatever the function is, it won't be relevant. It's a factorial function for sure. And now here comes the cute lemma. It's very easy. It says the following thing, that if I start from the same vertex A, I take two shortest paths, from A to B and from A to C. And if these paths have the same color signs word and the same length, then actually the endpoints are identical. These endpoints must be identical. And it's so simple that I can prove it. This will, of course, show that the number of vertices at prescribed distance d from A is upper bounded by the number of color sign words, which is, as I said, upper bounded by function. Why is this true? Well, let's do an induction. I mean, if the path is made of only one color, it starts from A, it goes into one of the directions, plus or minus, it's red, say. Of course, it ends in the same vertex. That's true. So it's true if the color sign words has length exactly one. Now, if I have paths which have the same colors and signs, but they might be different. I mean, the red part may be longer on P and shorter on P prime and so on. I still claim that they end in the same point. Why is that? Okay, the two paths start by the same color, say red. Assume that the red part of P is longer than the red part of P prime. Okay, what can I do? I look at this vertex that is the last on P prime colored red, and I say, okay, but this guy is blue. There, it's the same on the two paths. So what I can do is that in the first path, I can replace the red subpath by a blue one. I cannot make it longer. They are just shortest path. And then what I do is that I will restart the induction from here. I simply reduced a bit the distance, and I reduced the number of colors by one. So this is a very simple inductive proof that if you have a graph which is colorable by k shortest paths, in the sense that the edges are coverable by k shortest paths, then you have this lemma. If you start from vertex A, the number of vertices at the prescribed distance from A is upper bounded by a function of k. So that's my main combinatorial theorem for edges, and I can make it work. We can make it work for vertices as well, with a bit more technicalities, but it's doable. But at least this is very simple. So this proves our combinatorial bound, that our breadth research works fine, and then we do all these more complicated things that many people know to solve our problems in time FPT or XP. So that's why I dare call this proof cute. I mean, if we want this 3 to the k, the upper bound, it's a bit uglier. I'm not even sure I want to show it, and my time is running out. So let me be lazy. And basically, I mean, I don't need the previous proof. It works by pruning. Again, we take paths from A to different vertices at the same distance, and we take well-colored path, and we take their color signs words, and then we look at the first colors that we use. So here we say, okay, we use red and blue, and then we say, okay, but this first path has blue color, which is much further. And what we do is that we will, oops, I did it in the wrong direction, sorry. So it goes much further. Okay, so I did it on the red. So I say, okay, this path P2 has red after blue, but I want to make the red as long as possible. So I can replace this part by only red, and I can do the same for path P1. I can, since I have blue a bit further, I can replace the whole path by blue, and I replace this path by other group of paths, and then I regroup them by their starting letter, and I create some object that I call the branching tree, which satisfies some properties, and I count the leaves of the branching tree, and it boils down to 3 to the k. Okay, so to sum up, what have we done? I proved that if a graph is edge coverable by k shortest path, then the number of vertices at the same distance from any source is upper bounded by a function of k. I show the k to the k, and then I hand waved for 3 to the k. Just to show on this example that we cannot do much better. I mean, here is an example with k paths. It's easily constructed, and actually there are exactly 2 to the k vertices at a prescribed distance from this source. So I cannot improve, at least not in this direction, to something better than exponential. So okay, it works for edge coverings. It also works for vertex coverings, and as a algorithmic consequence, the algorithmic problems are FPT if the terminals are given, and XP if the terminals are not given and need to be guessed. So okay, some questions. The frustrating question is, what about problems without terminals? Are they FPT? Is it something that we overlooked? Or maybe should we have a W1 hardness proof? So there are under some classic hypothesis, one can show hardness for fixed parameter tractability. And it's not so clear.
You mean with terminals?
So with terminals, they're FPT. Without terminals, I don't know. Are they FPT or are they W something hard? If you give me the terminals, everything is FPT. If you don't give me the terminals, I don't know. Either I guess the terminals or I cannot say anything more. And honestly, I have no clue. I mean, I would, if I had to bet a beer, I would bet on W hardness. But maybe we were too lazy. We briefly discussed with a colleague. Actually, many problems, even on bounded tree, with if we play with distances, many problems become W hard for bounded tree. So it's not clear to me. The other question is, what about the best upper bound? I said that if G is covered by K shortest path, then its tree width is at most 3 to the K. Okay. But the worst examples we have are actually that their tree width is actually polynomial. I gave here an example, and I said, okay, if you do a BFS, then you get exponentially many vertices at the same distance, but you can retrieve another tree decomposition, even a path decomposition, which is of with K. We only have examples which are quadratic in K. Okay, we didn't dig too hard, but I would rather bet on polynomial bounds. And another maybe funniest point. So I find this problem so natural, and it seems that they're not that studied in the literature. Maybe, I mean, I don't know of any applications of this problem. So if you know of any, I would be happy to hear it. Okay, so I'm done. Mulțumesc.